Do you know what the name of this concept is?
Concept?
Do you know what the name of the symbol is?
Omega.
So the symbol is called omega. That's right. Do you know what the name of the concept is that the instructor is using that for?
No.
So this is what's called the angular velocity.
Okay.
Maybe we should compare it. Do you know what this symbol stands for?
Velocity.
So this is just the regular velocity.
Okay.
You might call it the linear velocity to distinguish it from the angular velocity.
Okay.
What are the units for this concept?
Meter per second.
Those are the SI units. Do you know what the SI units are for this concept?
It's theta. No, I have no idea. Was it theta over? I don't know.
Okay, you might have been on the right track there. So the units are radians per second.
Oh, radians. Okay.
Do you know what a radian is? A radian is a way of measuring an angle.
Okay.
Does that sound familiar to you?
Yeah.
A radian is a way of measuring an angle. So the key thing we just have to keep in mind is how many radians are there in a circle?
2 pi?
That's right. So the key to understanding this concept is just to remember that a circle is 2 pi radians.
Okay.
So let's say I tell you that, let's say we have an object that's moving in a circle, and let's say that its omega is 6 pi radians per second. Do you have any idea what that means?
In every second it will have moved 6 pi radians.
Excellent, that's right. So, first of all, we could write it like this. Instead of saying every second, what's the number we can put down here?
1 second.
We could say in 1 second it would move 6 pi radians. Good. Can you phrase that so that it's a little bit easier to understand? Can you interpret that without using the word radians? What does that tell us in simpler terms without using the word radians?
It will go 6 pi in 1 second.
6 pi what? So that doesn't quite work. 6 pi doesn't mean anything.
Okay.
How many circles is it going in 1 second?
Oh, it will go 3 circles in 1 second.
Isn't that a lot easier to understand?
Yeah.
So you asked me to explain what omega means, so now we've explained what omega means.
Okay.
It's just telling you, it's just a fancy coded way of telling you how many circles you're doing per second. So we could say that this really means 3 circles per second. So the key is just to keep in mind that a circle is 2 pi radians.
Okay.
If you keep this in mind, you should always be able to interpret what omega is telling us. So for example, let's say that another object has an omega of, say, 10 pi radians per second. What does that mean in simpler terms?
It would be, in every second it will have gone 5 circles.
So it really means 5 circles per second.
So how would you use this in the key, instead of A for circular motion, instead of saying V squared over R, he said the omega R. Omega squared R.
Okay. Well, let's try to work that out step by step, and that's important. So going back to this was 5 circles per second. Now, oftentimes instead of saying circles per second, it would be more fancy to say 5 revolutions per second.
Okay.
So that's a common way this is interpreted. This means 5 revolutions per second.
Okay.
But you could say circles too.
Is the revolution the same as period or no?
That's another important thing for us to talk about.
Oh, okay.
Okay, they're related but not quite the same thing.
Okay.
So let's say that omega was pi radians per second. What does that mean?
Means it's going half the circle in 1 second.
Yeah, and every second it goes half a circle. Or you could say half a revolution per second. Half a circle or half a revolution per second. examples then in your notes?
Yes.
So what are the SI units for omega?
Is it radians or something?
That's right. So that's the first step to understanding any concept. We can't learn anything about a concept until we know the units.
Okay.
So what I just tried to convince you of is that if you know omega in radians per second, you could find omega in circles per second.
Okay.
All you have to do is remember that one circle is how many radians.
It's 2 pi.
So we have a little flow chart here. If we use this equation, we can go from omega in radians per second to omega in circles per second.
Okay.
This is how you'd have to do it in a formula, but this is easier to interpret.
Okay.
Now we can talk about the concept of period. So again, let's consider an object that's moving in this circle.
Okay.
You know what the definition of the period is? What does the period tell us about this object that's moving in the circle?
I don't know.
Okay. Do you know what the symbol is for period?
No.
So a good symbol would be capital T.
Okay.
The period tells you how much time it takes to make one circle. The period tells you how much time it takes to make one circle.
Oh. Okay.
Or how much time it takes to make one revolution.
Is it in seconds?
Could be, that's a good point. So we could say the units, what would be good SI units?
It would be radians or... just circles over a second.
What would be the units for period?
Oh, for period? 2 pi?
What would be the units for period?
Um,
Not sure? Okay, I was just saying that because you just told me what the units were.
okay, so radians over seconds.
Well, no, earlier you said that would be in seconds. Remember I asked you, I said that the period was how long it would take to move one circle, and you said, oh, that would be in seconds.
So radians in...
No, seconds.
Seconds? That's it?
Why not? Well, so the period tells you how long it takes to go one circle.
So within itself, it just tells you. It doesn't...
That's the meaning of the period.
Oh,
So the period tells you, like the velocity tells you how fast something is going, the displacement tells you how far something has gone, the period tells you how long it takes to make one circle.
Okay, so I'm so used to like fractions
Okay,
and stuff
right.
that I was like, that doesn't make sense. okay, so it has the meaning within itself. So it would be seconds.
That's right, so the units here would be seconds. So the period is the time it takes the object to complete one circle or one revolution.
Okay.
Now actually, maybe we're kind of on the right track there, because actually if you think about it, you could write this as a fraction. Seconds per what? The period tells you how many seconds per what?
Per revolution?
Yeah, that's right. So it's really telling us seconds per revolution or seconds per circle.
So is it the opposite of the other one in the middle?
It looks like this. We have to be a little more precise. What do we mean by opposite? But yes, you're on the right track. So let's say that we know that omega is, say, let's say that we knew that omega was 3 circles per second. Do you have any idea how could we figure out the period?
It would be 1 second over 3 circles.
Then what? How would we calculate the period?
so it would be 1 second over 6 pi.
It sounds like you're going back to radians. It sounds
Yeah.
like we might be overcomplicating things
No?
here.
Uh-huh.
It's not because we don't want the answer to be in radians.
Oh, we
want
don't
the
want
answer
it.
to be in seconds or in seconds per
Okay.
circle.
It would be 1/3. It's
So what's the answer?
1/3.
What are the units on that?
Second per circle.
That's
Oh,
right.
this is circle.
So circle here is kind of like an optional unit.
Okay.
You could say the units are seconds or seconds per circle.
Okay.
Usually people say seconds, but I like to say seconds per circle because it makes it easier to see how to calculate it from this.
Okay.
So you could say this is 1/3 of, so the way we figured it is by using the units. This is 1/3 of a second per
Okay.
circle.
Okay.
Or you could just say it's 1/3 of a second.
Okay.
Doesn't that make sense?
Yeah.
In 1 second, how many circles does this make?
In 1 second, 3.
So doesn't it make sense that to make 1 circle would only take 1/3 of a second?
1 circle. Yeah.
In fact, you can see it's moving really quickly.
Yeah.
This is something that's moving very quickly.
Yeah.
Okay. All right. So now we were learning how to go from omega to period here.
Mhm.
Basically, all you have to do is just take the reciprocal, right?
Okay,
Because
yeah,
the units are
exactly.
reciprocals.
Yeah.
These are reciprocals, so if you take the reciprocal of this, you'll get this.
Okay.
So one of the things that you said in your email that you were having trouble with was finding the period.
Yeah.
So now we're seeing how we can use omega to find the period. Hopefully you can see, yeah, all right. So, but how would you change this to a decimal?
It would be point. Oh my god, it would be 0.3, right?
Okay, what process would you use to change it to a decimal?
What do you mean? So I divide 1 by 3.
Just wanted to make sure you did that. Yes, that's right. So the way we change this to a decimal, we do 1 divided by 3. All right, that would be 0.3333.
Yeah.
Okay. So now let's do another example. Let's say that the omega for the object is pi over 4 radians per second.
Okay.
Find the period. Let's do this on that tablet. How would you do this? I'll give you some more space.
Pi over. I mean pi. Or radians per second. Okay. Okay, so pi over 4 means it would be 1/4 the so half of the circle. So is it here? Okay, yeah. So would be how much of the whole circle would be 1/8 of a circle? So in 1 second it will have gone 1/8 of a circle. Which is 8. Does that make sense? No? Yes? No?
So what's your answer?
8. 8 seconds?
Okay, so let's write down that answer. What does that mean in words?
It means it takes 8 seconds for it to go over the whole circle.
Okay, you could say 8 seconds or 8 seconds per circle.
Okay. 8
Okay.
seconds per circle.
So let's review those steps. So first of all, you kind of started over here.
Yes.
So we had to change this into circles per second. Now the way I would do that is I would use a standard unit conversion approach.
Okay.
how many radians are there per circle?
How many radians per circle? 8. Is it?
Take your time. How many radians per circle?
2 pi. Yeah.
So what would be the conversion ratio that we would use? What number goes on the top and the bottom?
So 1 circle, 2 pi.
Okay. Do you know how to simplify this? What do you get when you simplify?
So you cross off radians, which you'll get, you cross off part so 1 over 8. The top, bottom, right? No, top. And then 1 over 8 circle seconds?
Okay. Is that what you got when you did it on your own?
No, I got 8
Oh, well.
seconds per circle.
Okay. So, you see how I got this?
Yeah.
Good. And how do you simplify this fraction? What's this really mean? This really means pi over 4.
4 times 1 over 2 pi.
Because dividing by a fraction is the same as multiplying by the reciprocal. So this is 1 over 8 circles per second.
Okay.
But then, you did the next step. You kind of did this in your head and you changed that into seconds per circle.
Yeah.
So how would you change this into seconds per circle? Well, this would be 1 second for 1/8. So the period would be this.
Okay, and then use.
And then how do you do this? Well, this is 1.
1 times 8 over 1.
1 divided by 1/8 is 1 times 8, right? Because the way you divide by a fraction is by multiplying by the reciprocal. So I think I got the same answer that you did?
Yeah.
Okay, so you did get the right answer. The method you used wasn't wrong, but it's good to see maybe a little bit more systematic way of working it out. The key is, so for me, I just do this as a unit conversion. There's 2 pi radians per circle. So, and this unit conversion, if you know the number of radians per second, you should always be able to figure out number of circles per second. Okay, like I said, the way you did it wasn't wrong, but maybe this is a little more systematic.
Yeah, more. You can't make mistakes here.
So did we finish the problem?
Yes.
What was the answer?
8 seconds per circle.
What does that mean?
It means in 8 seconds it will have gone through 1 circle.
That makes sense because notice it took, in 1 second, it only did 1/8 of a circle.
Yeah.
Since it did 1/8 of a circle in a second, it takes, so now this is going much slower than before, right?
Yeah.
So it'd be going 4 seconds to go halfway around, and then 8. So it was going about that path around the circle.
Okay.
Okay, that's a more realistic path maybe than the ones we had before. Okay, so that's one of the things you said you were having trouble with, finding the period.
Yeah.
So here's how you can use omega to find the period. This isn't the only way. If you understand intuitively what's happening here, there's a bunch of different ways to use this information to find the period, but that's one good systematic way. Can I erase this?
Yes.
Now what's the name of the concept that this symbol stands for?
Angular velocity.
Good. And this?
Linear velocity.
So next we need a way to connect these two ideas. We need a way to go between these.
Okay.
Well, So let's say we're thinking about circular motion. Well, what does it mean if r is getting bigger? What does that just mean?
And means we have a bigger, we're getting a bigger circle.
So now we're considering a bigger circle.
Yeah.
That's right. Let's say you move to a bigger circle but hold omega constant. So it would be like, I guess it would be like this.
So it will take longer to go through that circle.
So we're going from this smaller to this bigger circle.
Okay.
But now, let's say we hold omega constant.
Okay.
So that means it won't take longer, will it? Because we're still doing the same number of circles per second, right?
Okay.
So what's going to happen to V? If we're moving to a bigger circle, but we're trying to hold omega constant, what's going to happen to V? Will it go up or down or stay the same?
Go up.
That's right. How do you know?
Because we're moving faster.
How do you know we have to move faster?
Because we're covering more distance.
That's right. And we're trying to do the same number of circles per second.
Okay.
Remember, omega could be thought of as circles per second.
Okay.
If we're trying to do the same number of circles in a second, but the circles are bigger, then we need to have a faster v.
Okay.
Hopefully this helps you see the difference now between omega and v. Omega can stay the same while v changes if we just move to a bigger circle.
Okay.
So now that should help us to get a formula. So when r goes up, what happens to v?
Goes up.
So do these two variables move in the same or opposite directions?
Same.
So where would it make sense
On the top.
to put r, on the top or on the bottom of this fraction?
Up.
To make sure, because this way now this shows that the bigger r is, the bigger v is going to be. Okay, so this is another useful formula. Remember, our goal was to find a way to link up the linear velocity with the angular velocity.
Okay.
All right, and I didn't prove this formula, but I tried to show you that it makes sense, because I showed you this is just saying that if you move to a bigger circle, but you want to do the same number of circles per second, you got to move faster.
Okay.
So now we can continue our flowchart. I didn't leave myself enough room. But here we can put v. And then what's the formula we can use to move between v and omega?
V and omega.
What's the formula we'll use to move between?
RW. So it would be R between V and omega.
What's the formula that we can use to move between these two concepts?
V equals R omega.
That's right.
Okay.
Now, most of the formulas in this class are really just about magnitudes, and that's true for this formula too.
Okay.
So why don't we put in some dots to remind ourselves that we're usually just going to plug in positive numbers here. We're just going to use this for magnitudes. If you need to know the sign, you should be able to figure out the sign of these things on your own.
Okay.
So I hope you agree now, if I told you the v, would you be able to figure out the period?
Yeah, basically.
How?
So I will figure out omega first.
Using what?
Using V equals R omega.
Right, and then we just went over a systematic method for going between these. Okay? Alright, so that's another way that you might find the period. Although you shouldn't really need, if you know the v, and there's an easier way to find the period. I guess it's pretty much the same as we were doing this. So here, notice here we're assuming we're moving at constant speed.
Okay.
Right? You see this formula assumes that we're moving at constant speed because there's only one v. So we're assuming constant speed in this table.
Okay.
So we could just use distance equals v times t.
Mm-hmm.
So if you solve this for v, you get distance this. So how would you use this formula to figure out the period?
Distance over V.
How would you use this to figure out the period?
I will use, distance.
Forgetting about the flowchart, just using our common sense. What does the period tell you?
It's telling me the distance I'm covering. It is the period, isn't it?
What does the period tell us?
the time it takes to go through a circle.
That's right. It tells
So
us how
if
long
the-
it takes to complete one circle.
Okay.
So how would we use this formula to figure out the period if we knew v?
So d would be 2 pi, right? And then t.
What goes on top?
2 pi,
Why 2 pi?
because it's a circle. It's this thing. No.
So it's the circumference, right?
Yeah.
So what goes on top?
R squared. No, I mean 2 pi. 2 pi r. 2 pi r.
That's big. That's a lot different than 2 pi, though,
Yeah,
right?
yeah, yeah.
Okay. So if we want to know the time
Okay.
to make one circle,
Okay.
this would be the distance for one circle.
Okay.
So my point is, this is another way to figure out the period that just
Okay.
links these up directly. In fact, I guess I could. So you could, if you know v, you don't have to go through all this rigmarole.
Okay.
You can just use common sense to say, well, the distance is the circumference, and divide by v to find the period.
Okay.
So what's the formula that relates this concept and this concept?
V equals, T equals V over, T equals D over V, which is circumference of this circle over.
So what would we plug in for t in this particular problem?
The second per circle? What do you mean?
Well, here we're trying to find the period. And what's the symbol for period?
T, capital T.
Right. Do you see the difference between these? This stands for any time.
Okay.
And this stands for the time to complete one circle.
Okay.
So it's important to distinguish between uppercase and lowercase letters.
Okay.
This means any time. So this is a formula that would work for any time and any distance. But we can apply it here. If we want to figure out the period, what goes on top?
The same D over 2 pi r over V.
That's right. So here would be a shortcut way to go from V to the period.
Okay.
Okay, and now when we're moving in a circle, we were saying moving this way. We would have our tangential and radial axes. So now this doesn't stand for time, it stands for tangential.
Okay.
And then we can apply Newton's, and then we know we have a special formula for the radial acceleration. So what's our formula for radial acceleration?
A equals mv squared over r.
What's on the left side here?
AR.
So what goes on the right side?
V squared over r.
Okay, good. So this is our formula for the radial acceleration. So we could extend the flow chart like this.
Okay.
So what's the formula that connects these two ideas?
V squared over r.
Good, so what's the complete formula?
A sub r equals V squared over r.
Good. Good.
Okay.
And then we can apply Newton's second law. What's Newton's second law for the radial component?
Would be sum of forces of radial component equals m times radial acceleration, A sub r.
Good. Here's where the m comes in.
Okay, yeah, I can.
Good. Now, the next thing we would do though is what are we going to plug in for A sub r?
V squared over r.
Here's that mv squared over r that you were thinking of before. that's where the m comes in. So this is the formula for acceleration, but if you plug it into Newton's second law, you get the m.
Yeah.
Okay, good. So, you just plug in like that.
Okay.
All right, so we've already done a bunch of circular motion problems,
Okay.
right? So, do you see if you were doing a circular motion problem, you could use this equation to find v.
Mhm.
And then could you find omega?
Yeah.
How?
Use instead of v.
If you already know v, how would you if you used this already to find v, how would you find omega?
So I'll find omega by v over r.
That's right. So, once we know v, we can find omega.
Yeah.
All right, so my point is, I think you might have been really overcomplicating the omega problems.
Okay.
You can just solve for v.
Okay.
All right, you can just forget about omega and just find v. And then if the problem asked you for omega, you could just use this one formula. So all you really need to connect this with everything we've already learned to do is just this one formula.
Okay.
If you just know this one formula, then you can just solve the problem in terms of v.
Okay.
Right? And then at the end, you can make it into omega.
Okay.
Or on the other hand, let's say the problem told you omega. If the problem tells you what omega is, how can you use this formula?
I will solve for v.
Do it using what?
R times omega.
That's right. So if the problem tells you omega, does that mean that we can't use this formula anymore? No, it's no problem. You just use this one little equation, and then you know v, and then you can just do the problems the same way as before.
So I don't have to use omega squared r.
You don't have to. No, that's right. So one thing we're trying to show in the tutoring is oftentimes if you're systematic, the problems are a little simpler than they might seem.
Yeah.
I think you might have thought that omega was like a whole new type of problem. So omega is not a whole new type of problem. It's just one more concept that just can be added on to what we already know about. If you can solve the problem for v, you can always find omega at the end, just using this formula.
Even if they give me t, I can find omega or v.
That's right. If they give you the period,
yeah.
then you could go this way or this way to find v, and then you can still plug into Newton's second law. So the point is, it's still a Newton's second law problem. Okay? We still want to use this basic approach. Now, just so I can show you what your instructor was trying to do here, what would you get if you, how can we write this equation in terms of omega? Can you think of any way to get rid of the v and write this in terms of omega? How would you do that?
M times...
Let's write the whole equation.
Okay, so sum of f sub r equals m times, so omega was, okay, so r omega squared
You can
over
write it out.
r. R omega squared over r, which is m r squared omega squared over r, which we cancel. Okay. Makes so much sense.
Come out right. Okay, good. So, so we can see now we have another version of Newton's second law. So I don't know if you realized this when your instructor mentioned it in class, but this is just another version of Newton's second law. It's the same exact equation. We're just using this key formula here to replace v with r times omega. Is this the equation your instructor gave you in class? Does that look familiar?
R omega squared, yes.
mr omega squared? Did you
Yes.
get that right? So v squared equals, it's good that you squared both the r and the omega. That's important. So then the r's cancel. So that seems right. So if you want to do it, if you wanted to, you could use this equation.
Okay.
If you want to, you can use this equation. just keep in mind, it's not a fancy new, brand new equation. It's just the normal Newton's second law, just making one little substitution. So if you want to, you can use this equation, and then you would just solve it the way you would do any Newton's second law problem.
Okay.
Or, if you want to, you can just stick with this equation and find omega at the end by using this. So the key thing is, I think the key thing you might not have picked up from in class is that there's a simple way to go between v and omega. There's a simple way to go between them. Okay, so for solving problems, this equation is very important.
Okay.
And then the other thing we also tried to go over is what omega means. And we saw that it's just a fancy way of telling you how many circles you're going through per second.
Okay.
Because if you know how many radians you're going through per second, and you know there's 2 pi radians per circle, then you know how many circles you're going through per second. And we also saw how you could use that to find the period.
Yeah.
Or remember, you don't even have to think about omega. You could just say that the period is the time it takes to go one circumference. So you could just find the period the old-fashioned way using this formula. All right, so I guess things got a little complicated, but I tried to put kind of a flow chart on the board that shows how all these different concepts are related to each other.
I'll write the whole thing in my cheat sheet.
Okay. These videos are offered on a pay-what-you-like basis. You can pay for the use of the videos by making a monthly pledge at my Patreon page. Or you can make a one-time payment by using the PayPal donate button on my website. Thank you.